Hello and welcome to Dr. Jim's Structures class, where we do structures by example.
Man's practicing fuzzy math again.
This is the second video in a two-part mini-series on distributed loads on beams. The previous video introduced distributed loads by showing how to draw the axial force, shear force and bending moment diagrams for the simply supported beam. If you'd like to watch that video, click the link on the screen. This video analyses a simply supported beam carrying a point load and a uniformly varying load, often referred to as a UVL. So, let's get to it. The beam spans 6 meters and has a knife edge support at A and a roller support at E. It carries an upward load of 120 kilonewtons at B and a downward distributed load that varies linearly from 0 kilonewtons per meter at C to 90 kilonewtons per meter at D. As usual, we will start by finding the reactions. Draw a free body diagram bubble that cuts the beam away from its supports. The purple lines represent the cuts, and these cuts expose the unknown reactive forces. If this makes little sense to you, then click the link on the screen to find out more about cuts, free body diagram bubbles, and all sorts of cool stuff. Next, remove the supports and replace them with the forces that have been exposed by the cuts. Dr. Jim's video Random Thoughts 2.1 showed how to simplify dealing with distributed loads. The video showed that 1. A distributed load can be replaced by a single point load. 2. The magnitude of the equivalent load is equal to the area under the distributed load. 3. The equivalent load acts at the centroid of the distributed load. The load is triangular, so its area is 1/2 base times height. That is 0.5 times 2 meters times 90 kilonewtons per meter. That is 90 kilonewtons. The load acts at the centroid of the triangle, i.e. 3.333 meters from A. If you'd like to watch the video on distributed loads, click the link on the screen. We can now apply the equations of equilibrium to the free body to find the unknown reactions. We're dealing with a plane structure, and this means there are 3 equilibrium equations available to us. These equations are commonly expressed as 1. Horizontal forces must sum to 0, 2. Vertical forces must sum to 0, and 3. Moments about any point must also sum to 0. Starting with horizontal equilibrium, we see that HA is the only horizontal force, and because horizontal forces must sum to 0, HA must be 0. Inspection of the free body diagram shows that taking moments about A will yield VE, the vertical reaction at E. And when writing down equilibrium equations, always say what you're doing. So start by stating the sum of moments about A equals 0 and that counterclockwise moments will be taken as positive. The resulting equation shows that VE is plus 30 kilonewtons. Next, some vertical forces to show that VA is minus 60 kilonewtons. It's negative because of the effect of the 120 kilonewton force at B. Replace the labels on the reactions with numerical values, noting that the arrow representing the vertical reaction at A has been turned around to lose the negative sign. Next, erase the calculations to free up screen space. If you want to see a more detailed video on finding reactions, then click the link on the screen. Plane beams and frames carry axial force, shear force and bending moment. These forces arise in the structural members in response to loads applied to the structure. It might help you to think of loads and reactions as external forces, and to think of axial force, shear force and bending moment as internal forces that arise in response to the external forces. Note that here the word force is being used in a generic way, as it includes bending moments and external applied moments, as well as linear forces. To proceed requires a sign convention for the internal forces and the structural elements. And here is a graphical representation of the sign convention we use. The boxes represent a thin element cut from the beam. And note, tensile axial forces are regarded as positive. Shear forces that try to spin the element counterclockwise are regarded as positive, and bending moments that put the top face of the beam into tension are regarded as positive. In other words, hogging moments are positive. The next step is to figure out what's going on inside the beam. In previous videos, we discovered the following universal truths about axial force, shear force, and bending moment diagrams. 1. Bending moment is 0 at the ends of simply supported beams. 2. Axial force and shear force are constant between loads. 3. Bending moment varies linearly between loads. 4. Shear force varies linearly under a UDL. 5. Bending moment is parabolic under a UDL. 6. A transverse point load causes a step change in shear force. 7. A transverse point load causes a change of the slope of the bending moment. These laws apply to all beams and frames, both statically determinate and statically indeterminate. In fact, these laws are gold dust, as they make drawing axial force, shear force, and bending moment diagrams an awful lot simpler. So, knowing these truths, pause the playback and think about the best strategy for drawing the diagrams. There are smart and not so smart ways to go about this task. This solution will be based on the approach outlined in the video Bending in Beams the Smart Way. If you'd like to watch that video, click the link on the screen. Inspection of the free body diagram shows there are no axial forces in the beam, so there's no need to draw the axial force diagram. Drawing the axial force diagram is not wrong, it's just not very interesting. Start by drawing baselines for the shear force and bending moment diagrams, and take this opportunity to drop faint vertical lines from the key points on the free body diagram. We will work left to right along the beam, calculating internal forces in the beam. To do this, we must cut the beam to expose the internal forces, so start by drawing a free body diagram bubble that cuts the beam just to the right of A. Now draw the free body defined by the bubble and label the unknown forces exposed by the cut. And here's a reminder of Dr. Jim's rules for calculating the internal forces in beams and frames. 1. Always assume the unknown internal forces to be positive. 2. Always explain what you're doing. For example, state vertical forces must sum to 0 and that vertical forces acting upwards will be regarded as positive. Do this to make checking your calculations easy, and besides, it's just good manners to do so. 3. Always take moments about the cut to find the unknown internal bending moment. By inspection, the axial force A is 0. The shear force S is plus 60 kilonewtons and the bending moment M is 0. Shear force is constant between loads, so we can make a start to drawing the shear force diagram. We're finished with the free body diagram, so it can be erased to free up screen space. This wouldn't be done if working on paper. Next, draw the free body diagram bubble that cuts the beam just to the right of B. The beam is cut to the right of B to find the shear force between B and C in addition to the bending moment at B. Draw the free body diagram for everything inside the bubble. Again, the unknown forces can be found by inspection. The axial force A is 0, the shear force S is minus 60 kilonewtons, and the bending moment M is plus 60 kilonewton meters. Plot these results on the diagrams. Now comes a tricky bit, the UVL. To find out what's going on under the UVL will necessitate setting up algebraic expressions for shear force and bending moment between C and D. Draw a free body diagram bubble that cuts the UVL x meters from A, then draw the free body diagram for everything inside the bubble. We saw in the video Random Thoughts 2.1, Distributed Loads, that a distributed load can be replaced by a single point load. If you'd like to watch that video, click the link on the screen. The single point load is equal in magnitude to the area under the distributed load, and it acts at the centroid of the distributed load. That all sounds complicated, but we'll see that all it requires is some basic maths. To make our work easier, we will draw an enlarged view of the UVL. The load is x minus 2 meters long, and we need to know the intensity of the load at its right hand end. This can be done by similar triangles, but for simple cases like this, logic is quicker and easier. Here's Dr. Jim's thinking. The UVL is increasing at 45 kilonewtons per meter. Think about it, 45 kilonewtons per meter. So after x minus 2 meters, the intensity of the load will be 45 times x minus 2 kilonewtons per meter. The equivalent load acts at the centroid of the triangle. That is, 1/3 of the way from the right hand end. Its magnitude is equal to the area under the load. The load is triangular, so its area is 1/2 base times height, and tidying up the resulting expression shows P is equal to 22.5 times x minus 2 squared kilonewtons. Copy what we've found to the upper free body diagram and erase the working to free up screen space. Next, looking at the free body diagram, write down the equations of equilibrium for shear force and bending moment x meters from A. Shear force is S equals 22.5 x minus 2 squared minus 60 kilonewtons. Now, taking moments about the cut, write down the expression for the bending moment. Tidying up the expression shows bending moment is 7.5 times x minus 2 cubed minus 60x plus 120 kilonewton meters. Note, these equations are good for all values of x from 2 to 4 meters. As we are sketching the diagrams, values will only be calculated at half-meter intervals. Draw a table, then tabulate the shear and bending values using the equations on the right. Dr. Jim used Excel to get the results, as he does not trust himself with a calculator. Other software such as Google Charts, MathCAD or MATLAB can be used. MathCAD is a wonderful tool, and there's a free version. Dr. Jim is a big fan, but that's for another video. Next, plot the calculated results on the shear force and bending moment diagrams. Finally, we need to find out what's happening between D and E. And here the universal truths make life very easy. Shear is constant between loads, and that truth allows the shear force diagram to be completed. The bending moment diagram is completed by knowing that bending moment diagrams are sloping straight lines between loads, and that bending moment is 0 at the ends of simply supported beams. It's unlikely that the minus 64.69 kilonewton meters is the maximum sagging moment. So we need to figure out what the maximum moment is. To do that, we will need the expressions for shear and bending, but the rest of the working can be erased to free up screen space. Next, expand and tidy up the expression for shear. The roots of the resulting quadratic equation will give the values of x where the shear is 0. The standard solution for a quadratic is minus b plus or minus the square root of b squared minus 4ac all over 2a. and plugging in the coefficients from the shear equation yields x is equal to 3.633 meters, or x is equal to 0.367 meters. Obviously, the smaller root is inapplicable as it does not lie under the UVL, and plugging 3.633 meters into the moment equation shows that the maximum moment is minus 65.32 kilonewton meters. Mark the maximum bending moment on the diagram and tidy up the screen. You will have noticed that the screen has been tidied up at various points during the analysis to free up screen space. This is fine for an educational video like this, but when solving on paper, all the working should be retained. It might be worth marks after all. And that concludes the analysis. If you would like free, printable, annotated notes for this video, then swing by Dr. Jim's website at drjimstructures.com. In the next video of this mini-series, Dr. Jim will analyse the beam using LinPro, a free, lightweight frame analysis program. To watch the LinPro analysis video, click the link on the screen. Well, thanks for watching. If you found this video useful, please give it a like and feel free to comment. Your feedback is appreciated. Bye for now. Hope to see you again soon.
Phony numbers.
If I could respond to that.
Let me just tell you what the facts are.